Hello and welcome. In this video, we are going to take a deep dive into one of the most fundamental concepts in all of electronics and circuit analysis, electrical sources. These are the components that provide energy to a circuit, making everything else work. We will break down every type of source, from the simple to the complex, so that by the end, you will have a solid understanding of how they are classified and how they behave. Let's begin by looking at the overall classification, as shown in our chart. At the very top, we have the main category, sources. All electrical sources can be divided into two primary families, voltage sources and current sources. A voltage source is a device that is designed to maintain a constant voltage, or potential difference, across its two terminals, regardless of the current that is drawn from it. Think of it like a water pump that always maintains a specific pressure difference between its inlet and outlet. A current source, on the other hand, is a device designed to supply a constant amount of current, regardless of the voltage across its terminals. You can imagine this as a regulated river that always delivers the same volume of water per second, no matter how wide or narrow the riverbed gets downstream. Now, both voltage sources and current sources can be further divided into two more categories, independent and dependent. An independent source is a source whose value is fixed. It does not depend on any other voltage or current anywhere else in the circuit. It has a specific, predetermined value, like a 9-volt battery. A dependent source, also known as a controlled source, is different. Its value is not fixed. Instead, its output voltage or current is controlled by another voltage or current somewhere else in the circuit. These are incredibly important for modeling active components like transistors and amplifiers. Let's go one level deeper. The independent sources, both voltage and current, can be thought of in two ways, ideal and practical. An ideal source is a theoretical model. It's the perfect version of a source that exists only in calculations and on paper. It has no real-world limitations. A practical source is a more realistic model. It takes into account the physical limitations and imperfections that all real-world sources have. Finally, looking at the dependent sources, they are categorized based on what controls them and what they produce. This gives us four distinct types. First, a current-controlled voltage source. Second, a voltage-controlled voltage source. Third, a current-controlled current source. And fourth, a voltage-controlled current source. We will explore each of these in detail. For now, just remember this complete hierarchy. Let's start our detailed exploration with independent voltage sources. An independent voltage source is defined as a source where the terminal voltage is not dependent on any other voltage or current source in the circuit. Its job is to provide a steady voltage. First, let's look at the ideal voltage source. The circuit symbol is a circle with a plus and a minus sign inside, indicating the polarity. The voltage it provides is labeled as V. The key characteristic of an ideal voltage source is that its internal resistance, which we call R sub S, is equal to 0 ohms. This means there is absolutely nothing inside the source to impede the flow of current. Because of this, the terminal voltage, which we call V sub T, is always exactly equal to the source's internal voltage, V. This is perfectly illustrated by its graph. The vertical axis represents the terminal voltage, V sub T, and the horizontal axis represents the current, I, being drawn from the source. For an ideal voltage source, the graph is a perfectly horizontal line. This shows that no matter how much current you draw, whether it's a little or a lot, the terminal voltage remains absolutely constant. Now, let's move to the practical voltage source. This is our model for a real-world source, like a battery. The circuit symbol shows our ideal voltage source, V, but now it has a small resistor, R sub S, connected in series with it. This is the internal resistance. In a real source, this resistance is very small, but it is not zero. This internal resistance has a significant effect. When you connect a load and draw current, the current must flow through the internal resistor R sub S. According to Ohm's law, this creates a voltage drop across that resistor. This voltage drop is subtracted from the ideal source voltage, V. Therefore, the terminal voltage, V sub T, that you can actually measure and use, is less than the ideal voltage V. The more current you draw, the larger the voltage drop across the internal resistance, and the lower the terminal voltage becomes. The graph for the practical voltage source shows this clearly. The vertical axis is terminal voltage, V sub T, and the horizontal axis is current, I. When no current is being drawn, at I equals 0, the terminal voltage is at its maximum, equal to the ideal voltage V. However, as you start to draw more current, moving to the right on the horizontal axis, the terminal voltage begins to decrease. This creates a line with a downward slope. The slope of this line is actually determined by the value of the internal resistance. This is why real batteries show a lower voltage when they are powering a heavy load. Next, let's discuss the independent current source. The definition of an independent current source is that the current it supplies does not depend on any other voltage or current source in the circuit. Its purpose is to deliver a fixed amount of current. Let's start with the ideal current source. Its circuit symbol is a circle with an arrow inside. The arrow indicates the direction of the current flow, and the value of the current is labeled I. The defining feature of an ideal current source is that its internal resistance, often called a shunt resistance or R sub SH, is infinite. This resistance is modeled in parallel with the source. An infinite resistance means that it's like an open circuit, no current can leak or be diverted through this internal path. Therefore, all of the source's current, I, is forced to flow out to the external circuit. The terminal current, I sub T, is always exactly equal to the source current, I. The graph for the ideal current source plots the terminal current, I sub T, on the vertical axis against the load resistance, R sub L, on the horizontal axis. The graph is a perfectly horizontal line. This visually represents that the current supplied by the source is constant and does not change, no matter what value of load resistance is connected to it. It will always push out the same amount of current. Now for the practical current source. This model represents a real-world current source. The circuit symbol shows the ideal current source, I, with an internal shunt resistance, R sub SH, connected in parallel with it. For a practical source, this internal resistance is very large, but it is not infinite. Because this resistance is not infinite, it provides a path for some of the source's current to leak internally. The current from the ideal source I reaches a junction and splits. Some of it, the terminal current I sub T, goes to the external load, and some of it leaks through the internal resistance or sub SH. The amount of current that leaks depends on the voltage across the terminals. Let's look at the graph for the practical current source. The vertical axis is the terminal current, I sub T, and the horizontal axis is the load resistance, R sub L. As the load resistance increases, the voltage across the terminals also tends to increase. A higher voltage across the internal shunt resistor causes more current to be diverted through it, leaving less current available for the load. Therefore, as the load resistance or sub L increases, the terminal current I sub T decreases, resulting in a line with a downward slope. Now we move on to the fascinating world of dependent sources. Dependent sources are fundamental in electronics for modeling the behavior of active devices like transistors. Their symbol is always a diamond shape, which immediately distinguishes them from the circular independent sources. Their output is not a fixed value, it is determined by a voltage or current somewhere else in the circuit. There are 4 types. Let's start with number 1, a voltage-controlled voltage source, or VCVS. The name tells you everything. Voltage control means its behavior is dictated by a controlling voltage, which we'll call V sub C. The voltage source means its output is a voltage. The circuit symbol is a diamond with a plus and minus sign inside. The value of this dependent voltage, which we'll call V sub D, is given by the equation V sub D equals K times V sub C. Here, V sub D is the controlled voltage output of the source. V sub C is the controlling voltage from another part of the circuit. And K is the proportionality constant. Since we are multiplying a voltage, V sub C, to get another voltage, V sub D, the constant K must be uniless. It's a simple voltage gain factor, representing volts per volt. Second, we have a current-controlled voltage source, or CCVS. Again, let's break down the name. Current control means it is controlled by a current, which we'll call I sub C. The voltage source means its output is a voltage. The symbol is a diamond with a plus and minus inside. The equation for its output voltage is V sub D equals R sub M times I sub C. Here, V sub D is the controlled output voltage. I sub C is the controlling current from elsewhere in the circuit. The proportionality constant is R sub M. To get a voltage output from a current input, this constant, R sub M, must have units of resistance, measured in ohms. This type of source is often called a transresistance amplifier. Third on our list is a voltage-controlled current source, or VCCS. Voltage control tells us it's controlled by a voltage, V sub C, current source tells us its output is a current. The circuit symbol is a diamond with an arrow inside to indicate the direction of the current flow. The equation for the output current is I sub D equals G sub M times V sub C. Here, I sub D is the controlled output current. V sub C is the controlling voltage. The proportionality constant is G sub M. To get a current output from a voltage input, the constant G sub M must have units of conductance, which is the inverse of resistance, and is measured in Siemens. This is often called a transconductance amplifier. Finally, we have number 4, a current-controlled current source, or CCCS. Current control means it's controlled by a current, I sub C, current source means its output is also a current. The symbol is a diamond with an arrow inside. The governing equation is I sub D equals K sub I times I sub C. Here, I sub D is the controlled output current. I sub C is the controlling current. The proportionality constant is K sub I. Since we are multiplying a current to get another current, the constant K sub I must be uniless. It is a simple current gain factor, representing amps per amp. And that covers all the fundamental types of electrical sources. To summarize, we have voltage and current sources. They can be independent, with fixed values, which we model as either ideal, perfect, or practical, with real-world internal resistance. Or, they can be dependent, with their values controlled by another part of the circuit, giving us the 4 types, VCVS, CCVS, VCCS, and CCCS. Understanding these building blocks is absolutely essential for analyzing any electrical or electronic circuit. Thank you for watching.